Okay, good morning. Uh, Before we begin, just one announcement. So today my schedule is like completely tight, completely packed. As you all know, I'm in classes from 9 a.m. to 12 noon. And then today we have the events going on campus. So I have meetings, seminars, and I'm also hosting lab tours, and I'm meeting with, prospective new students. So my office hours, I'm going to cancel the ones that I have from 1 to 2:30, but I will be in my office from 4 to 5. Okay, so if you need, send me an email, reach out to me. I'll be able to answer emails on and off, during meetings and workshops and the tours. But I will also be available to students in my office between 4 and 5 p.m. I will also post an announcement on Canvas for students who are not here yet, but I just thought I'd let you know since you're here in person. Okay, all right, so let's get to node voltage analysis. What I want to do today is cover the theory, basically the method, the step-by-step solutions for node voltage analysis, cover an example problem, and then if time permits, I also wish to go over the homework for node voltage analysis. That homework is due Sunday night, so you have, well, a little bit less than 3 days. There are 3 problems in there. I'll go over all those 3 in class. If not, if you don't have enough time to go over it in class, what I will do is I will create a slide and I'll post it either on Canvas or on the class notebook. So students have a guideline of what to do. Sounds good? Okay. All right. So we stopped here where I introduced the topic of node voltage analysis. And to do a brief recap, it's an analysis technique, right? It's an analysis technique that allows us to solve for the unknown voltages and unknown currents in a circuit, right? Node voltage analysis specifically will require us to generate equations. We generate equations by applying KCL. Again, so voltage analysis, we generate equations by applying KCL, the current law. Okay. When you get to mesh current analysis, the current analysis would require us to apply voltage law, KVL. But again, that's, I'll repeat that when we get to mesh current analysis. For node voltage, NVA requires KCL. So we generate these equations, a set of linear equations, and then there are unknown variables in those equations. Those unknown variables will be or would be your node voltages. So depending on how many nodes you have in a circuit, you would have that many unknown variables, and how many unknown variables you have will require that many equations. So if you have 2 unknown variables, you need at least 2 equations to solve them. If you have 3 unknown variables, you need 3 equations to solve, and so on and so forth. So when we are first looking at a new problem or a new circuit, the first thing to do is identify all the nodes, right? We identify all the nodes. We choose a reference node. Then we apply Ohm's law, KCL to generate our equations. So here in this slide, I will go over how we will write out those equations. Okay, and then I will summarize all these steps in the next slide. So let's say we have a resistor in a circuit. That resistor has 2 terminals. It is connected between 2 nodes, A and B. So the node voltage at this end is VA, and at the right end is VB. So we have node voltages VA and VB. Okay. These are the assumptions you would make, or this is the setup of the problem you would do when you begin your analysis. Identify the nodes, label the nodes, label the node voltages, right? So A, B for this resistor, node voltage is VA, VB. And then the third step, kind of important, is you choose a reference direction and mark a current that is flowing through that resistor. Okay. So I would say identify nodes. I don't know why I wrote it there. Let's see, move it to the side. Identify the nodes. Label node voltages. And then indicate, or actually assume and indicate the branch current flowing through that branch of the circuit. Branch current simply means the current that is flowing through that resistor itself. Okay, so assume and I indicate the branch current that is flowing through the circuit. In this example of the single resistor, it would be this current I. Okay. Now, again, think back to chapter 1. When we begin analysis of any problem, we have no idea of the voltage polarity. We have no idea of the currents flowing in the circuit. So we make assumptions. So you're assuming, you're making an assumption here on which direction the current is flowing. It doesn't matter what you choose. Okay, the assumptions, as I've stated several times, the assumptions are based on rules. They are based on logic. But even if you go against a rule and you choose an opposite direction, your answer is not going to be incorrect. That is the most important thing. It doesn't matter what direction you choose. It doesn't matter what polarity you assign to a voltage. If you stick with that assumption from the top of the problem to the end, from the beginning to the end, your answer will be correct. And you can test it out by taking a single circuit and making different assumptions and trying to solve it different ways using this method, and it will all turn out to be correct. Okay, so you assume and indicate branch current. And so what I can write is VR, the voltage across that resistor, actually, I'm jumping one step ahead. Current I is noted as the current that is flowing through the resistor. When I apply Ohm's law, I can state I is VR over R. Is VR over R, Ohm's law. V equals to IR, I is equal to V over R. So the current I flowing through that resistor is the resistor voltage divided by the resistor R. Now, we express VR in terms of the node voltages at either end of that resistor. Okay, at either end. So what voltages do we have on either side of the resistor? Right, the node voltages VA and VB. Which end is higher? He says VA. How many of you say VA? How many of you say none? Or VB? Are they both equal? No, because you chose a direction for the current. If you chose a direction for the current, you are assuming or concluding that this end is higher, this end is lower. Current always goes from high to low for a current. So again, when you write a KCL, it will help you minimize your errors when you note everything down in your circuit diagram. So note everything down. Note down the node voltages, note down the current direction, and then once you note down the current direction, you note down the polarity of the voltage across that resistor. Since I am choosing my current going from left to right, my conclusion would be that the left end, VA, is higher than VB, so plus minus. If it's plus minus, I can express VR as VA minus VB. And that's it. That's all we need to do. We express each resistor in terms of the current that is flowing through it. We make certain assumptions. Then we simply express each resistor voltage and node voltage, plug in all the known values given to us. Resistor values will be given to us. They will be known to us. So we plug in all those values. We reduce it to form of linear equation. And then you generate as many equations as you need. Okay. So far, so good. Okay, so then the example below it has 3 resistors, and now we will see how we can apply KCL to generate equation for all 3 of them. So this is for sample A. Here, in the example with the 3 resistors, all the node voltages are given to us, VA, VB, VC, VD, right? In a problem statement, you may or may not be given the nodes. So again, if it's not, you identify the nodes, label all the node voltages, in this case, VA to VD, and make assumptions along with the current direction about the branch currents that are flowing through each resistor. So here we are given I1, I2, and I3. Based on these given current directions, or based on the assumed current directions, I can state current I1 is flowing from VA to VB. So VA is plus, VB is minus for resistor R1. Okay, for resistor R1, node A is higher than node B. So VA is plus, VB is minus. It's critical to understand this, otherwise your solution will be incorrect. Any questions? Okay. All right, I2. I2 I have coming down from the top, so point of entry plus, point of exit minus. So in this case, node B is higher than node C for resistor R2. Okay. Again, think back to, I think last week or the week before that. If you think about the node B, you might state, why is it minus, plus, and minus again at the same node, right? How can the same node have a plus and a minus? Again, they are not related to each other. It's describing just the resistor voltage. Just this, nothing else. And then finally, we have I3. I3 is going from the left, so point of entry is plus, point of exit is minus. Now we apply KCL. Apply KCL at node B. All right, apply KCL at B. What do we have? How many currents entering? I1 equals I2 plus I3. So again, that should be your absolute first step in writing out the equations. You apply KCL, whatever label you give to the currents, you write out that KCL expression. I1 is equal to I2 plus I3. Then you apply Ohm's law, and you can express I1 as VR1 divided by R1. The resistor voltage divided by the resistor R. So VR1 over R1, I2 is VR2 over R2, and I3 would be VR3 over R3. I would strongly recommend to not skip this step. If you look at most textbooks, they will not write out this step. I would strongly recommend do not skip this, especially when you're learning this technique for the first time. Okay, write this out. So help you in relating each resistor voltage to that circuit diagram. Okay. So now VR1 can be expressed in terms of the node voltages. What is VR1? How many of you agree? 1 thumbs up, 2 thumbs up, 3 thumbs up, 4. Anyone with a thumbs down? VA minus VB divided by R1. And then, of course, VR2 is the same. VB minus VC divided by R2. And VR3 would be VB minus VD divided by R3. Okay. Let's take a 10-second pause. You think on that. Let me know if you have any questions. Let's bring up the circuit diagram. There you go. Any questions? Does it make sense? Right now I'm going slow, so it probably makes sense, but you need to, again, when you do this for homework problems and the quiz and the exam, you need to do the same thing. Take it slow. Don't skip steps. This is just 3 steps. Write out the KCL expression, then apply Ohm's law, and then express each resistor voltage in terms of the node voltages. And then your answer would turn out to be correct. Now, from this point on, you plug in all the known values and reduce it to a linear equation. And we see that in the example problem. Okay. Okay, there are no questions. Let's summarize all the steps. So the first step is, of course, to identify all the nodes in the circuit, label all the node voltages. So I would add that here. Label all nodes and node voltages. Okay. Then you select a reference node. You select a reference node. And remember from last class, once you select a reference node, the value assigned to that node is 0 volts, because that is the common point of measurement for the entire circuit. So whatever your baseline is, you assign a value of 0 to that reference node. You select a reference node and you assign a value of 0 volts. Then apply KCL at each node, apply Ohm's law, and express each branch current in terms of the resistor voltage. Happened to my notes. Okay. Assign branch currents, assume direction for the branch current. That would allow you to conclude the polarity of the node voltages across each resistor. Then you apply Ohm's law and then express each resistor voltage in terms of the node voltage by noting the polarity of that voltage. And that's it. That's the summary. Now, one important note that I pointed out last class is choose one end of a voltage source as your reference. I believe I stated this. Yeah, I stated this here. Choose any node as reference, but yes, if you have a voltage source, choose one end of the voltage source as your reference, and that would automatically give you an answer for 2 of those nodes, right? If you have a voltage source, you choose one end as reference, so that's 0, and the other end would be the supply voltage. To keep things simple, choose the negative end of the voltage source or the common terminal as 0 volts as reference. So the other end, you would have positive Vs. All right, let's look at an example. How many nodes in this circuit? Ignore the ground that is shown. We don't care about that. How many nodes? 1, 2, 3, 4, 5, 6, 7, 8. How many of you say 8? Nobody? How many of you say 6? I would say higher the number of nodes, the more points you get. 6? How about 5? Maybe we should have a quiz about nodes. Speak up. Speaking up is not going to be a problem. 10? Okay, he says 10. Anyone with an even dozen? 5? I have 5. Anyone with 5? Going once? Going twice? It's not gone. It's not a trick. I mean, it's like the student's capability to identify nodes. So before I give you the answer, let me explain what a node is again. Again, this is the point of this is that learn, right? Students should learn. So A node is a junction of two or more components. A node can be a point, it can be a short wire, it can be a very long wire. If there is nothing connected between any 2 points, then the entire wire is a node. So now I ask again, how many nodes do we see in here? Six, three. You all tell me. Are the dots nodes? They just indicate a connection. But if there's nothing connected between two dots, it's still a wire. If it's still a wire, then it's still a node. So yes, that's exactly it. Node is where the voltage is the same. Remember I said when you plug a 100-foot extension cable into a power outlet, at the end 100 feet away, you would still expect 120 volts to come out. Electrically speaking, 100 feet away, that connection is still the same node as the power outlet. So the correct answer is 3. 1, 2, and 3. After I but after I stated the definitions, I think several students did say 3. So that is 3. It's a good exercise. It's not a verbal quiz, it's class participation. So I know it's early in the morning, you might be up late at night. I'm up late every night. I don't think I go to bed before midnight. So yes. Sure, yeah. So the question being asked is, how does it work as a node? So we see a connection from the current source. That connection goes uninterrupted to R3, also goes uninterrupted to R2, also goes uninterrupted to R1. The dots kind of throw people off because that's the way the circuit diagram is made. So it's nice and clean. Everything is either horizontal, vertical, thank you, vertical or horizontal. And so the circuit diagram looks very nice and clean and easy to draw out, easy to understand, right? When I use the word easy, it's kind of relative. But I could draw the same circuit diagram like this. Okay, there's a connection, the 2 resistors up top. I have another resistor right here. And then I have these current sources connected this node. Now this circuit diagram is not as nice and pretty to look at. Well, if you ignore my drawing skills. But again, you see what I'm saying, right? Everything's either horizontal or vertical when you draw a circuit diagram. And so you won't find something like this where something's at an angle. And so this is nicer, cleaner, it makes things easier to visualize. You have enough space to mark out the voltages, you mark out the currents and everything. But if you look at the diagram on the left, you can see now there's only one dot here, there's one dot here, and there's one dot down below right here. And so then it's easy to visualize or count the number of nodes on the left, whereas on the right, well, it takes a little bit more understanding. Does that make sense? Okay. All right, so let's the first thing to do is identify the nodes. We have done that. Let's label them. Let me see what I labeled in my notes. Okay, I'm going to label this end here as A, this node on the right as B, and this node on the bottom as C. Okay, A, B, and C. Yes. Sorry, what? Sure, yeah. Mm-hmm. That was going to be my next point. Very good observation. So the observation made by the student is R2 and R3 in parallel? Observation / question, and absolutely yes, they are in parallel. So before we begin our analysis, if it is a possibility, we can reduce the resistors in a circuit. And when you reduce the resistors in the circuit, we might end up reducing the number of nodes. In this case, it does not matter. We'll still have a variable, so you can do R3 and R2 in parallel, it's fine, but it doesn't reduce the number of nodes. But if you have a series connection, then a series connection will have a node in the middle. So if you have a series connection and you combine the two resistors, you have eliminated one node. Okay, so very good point. Okay, so I'm going to choose C as my reference node, right? Therefore, VC is 0 volts. So assign nodes, node voltages, choose a reference node, and now let me assign branch currents. So since we spoke about combining the resistors, let's go ahead and do that. Let me draw it out here. And I will call this R23. Keep things simple in that sense. It's a combination of 2 and 3 in parallel. So it's R2 in parallel with R3. I have a current source going up. I have a current source coming down. And they're all connected together at the end. C, VC is 0 volts. There is no voltage source in here, so we cannot have an answer for a node. Yes. There's a specific reason. Is because the answers we obtain from here are going to be negative. I will explain at the end. So once we find the final answers, I will explain what it means, and I will also explain if we choose what happens if we choose A as a reference and B as a reference. So right now we choose C as the reference node, so VC is assigned as 0 volts. I'll go ahead and mark out current directions. This is labeled as I1, the current source. That direction is already given to us. So I'm going to stick with that direction, and I'm going to say the current flows in this direction through R23, from left to right. If it's going from left to right, the voltage across that resistor will be positive on the left, negative on the right. So VR23 is the voltage across that resistor. Then, because it's going towards the right, I will assume that the currents through, this is R1 and this is R2. I should have left more space there. And let me make an assumption that both currents are coming down from the top. Okay, so this would be IR1. This would be IR2. And voltage across R2, I should have left more space. Let's see. Voltage across R2 would be VR2. Node C, B, and this current is coming down, it's I2. I also prefer to actually write out the values given to me in the circuit diagram itself. So I1 is given to me as 10 milliamps. So I write that here. I2 is 50 milliamps. And that's why I prefer large circuit diagrams. 1 kilo ohm, 2 kilo ohms. And of course, this is a parallel combination of, let's see, R3 and R2. So, oh, actually, this is R4, sorry. This is R4. Nobody noticed that or hesitant to speak out? That's not R2, that's R4. R2 is above. So this is 2 kilo ohms, and this is 2 parallel 10. Okay. 20 divided by 12. Okay, let's see. Do I have everything? I have VR4, VR23, VR1 should be here. Polarity plus up top, minus at the bottom. So let's do a recap. I identified all the nodes, A, B, C. I chose a reference node. So VC, voltage at C, VC is equal to 0. Then let's see. I assumed and identified all the branch currents. From the branch currents, I noted down the resistor polarities. And now I am ready to apply KCL. This is the problem setup. This is what I will ask you in the quiz on Monday, and then also on the final exam. Okay. Homework for node voltage is due on Sunday night. Quiz on Monday. We'll deal with the topic of node voltage analysis. So I will again, as I stated earlier, I will go over the homework problems in class if we have time. If not, I'll post a video or a slide about these homework problems. So let's apply KCL at A. And might go a little faster this time. KCL at A would give me I1 is entering the node, right? I1 is entering the node. Then IR23, I didn't mark that. Let's call this IR23. IR23 is leaving and IR1 is also leaving. So I1 is equal to IR1 plus IR23. Easy enough, right? Simple KCL. Then you apply Ohm's law. I1 is the current source. We have a value for this, so we leave it as it is. IR1 is VR1 divided by R1. And here this is VR23 divided by R23. R23 should be equal to, let's see, 2000 times 10,000. So 2 times 10 divided by 2 plus 10 gives me 20 divided by 12. 12 1s 1, 12 8 6 1666.667 ohms. I think that's correct. Calculator's out. Let me know if I make an error anywhere. This is 10 milliamps, so it's 0.01. And VR1, I'm ready to express in terms of the node voltages. VR1 is the voltage across resistor R1. R1 is connected to A and to C. So it would be VA minus VC divided by R1. R1 is 1000. I'm going to go ahead and plug in those values. And then VR23 would be VA minus VB. VA minus VB divided by 1666.667. So now, once you have plugged in all the known values, you can go ahead and reduce this expression. It's a set of linear equations, so you can solve this any way you want. You can plug this equation as it is into any solver, into your programmable calculators. I stated and I talked about MATLAB in last class. You can use MATLAB if you wish. Yeah, any way you want. Matrix determinants method, there are several ways to solve this. Okay. So when I reduce this, what I'm going to do is I will multiply everything by 1000. So multiply by 1000. So that gives me 10 is equal to VA. Remember, VC is my reference node, is 0 volts. VC is equal to 0 volts. So VC is gone. VA divided by 1000 times 1000 gives me VA plus 1000 divided by 1666 gives me 0.5999 VA minus VB. Okay, VA minus VB. So I rearrange the terms. My unknown variables are VA and VB. So I want the equation in this form. 0.599. No, actually 1.599. VA minus 0.5999 VB is equal to 10. This, yeah, made a hash of it again. I'm gonna give up. There you go. And this I'm going to refer to as equation 1. Okay, how are we doing on time? 9:45. Okay. All right, let's move things along. Now I will apply KCL at B. KCL at B gives me one current entering, IR23 enters B. Then I have two currents leaving, which is IR4 plus I2. I2 is my current source. I apply Ohm's law and express this current as VR23, voltage across R23 divided by the resistor. And then IR4 is VR4 divided by R4 plus I2. Express each resistor voltage in terms of the node voltages. VR23 is the same. It still remains the same. So it's VA minus VB divided by 1666.667. This would be VB minus VC divided by 2000. And this is 50 milliamps, so 0.05. 0.05. Now I'm going to multiply this times 2000. That gives me 1.1999 times VA minus VB equals VB plus 100. Rearrange the terms and you get 1.199 VA minus 2.1999 VB equals 100. And this is going to be equation 2. Solve these equations using any method you choose. Okay, any method you choose. So from here and from here, solve with any method. Solve with any method. Then I would obtain VA as minus 13.569 volts and VB as minus 52.857 volts. Are my answers correct or incorrect? We don't know. No confidence? Yes. If it's minus, it doesn't mean it's incorrect. It just means, well, not quite opposite. It just means that, well, opposite, yes, but remember, we chose a reference node at the beginning of our analysis. So what this means is both nodes A and B are below node C. And so if I draw a two-dimensional graph and plot these 3 points, I should get something like this. Let's see, this would be C. C is somewhere here. So this is C, which is equal to 0 volts. A would be somewhere here, which is about 13.569 volts below C. Yeah, there's no minus. It's a graph. The graph automatically shows me that A is below C. Mathematically, if I'm writing the value, I would put a minus sign to indicate the lower level. And then B is somewhere here. So this is B. And this has a value of 52.857 volts. And so that's what it means. Yes. Well, no, not quite, because these are still node voltages. They are not resistor voltages. We can calculate the resistor voltages from these node voltages. Okay, so for instance, an example, if we go back to the diagram, what do we see? R1 and R4 are connected, well, they're not parallel, sorry. R4 is between node B and C. So you would plug in the values of B and C in there, VB minus VC. Our direction that we chose is that B is higher than C. Okay, so we still stick with that assumption. We do not change that assumption. If you change that assumption, then your resistor voltage will turn out to be incorrect. You do not change this assumption. Your assumption is that current is flowing from B to C. So resistor voltage VR4 will still be VB minus VC. VC is still 0 volts. Okay, VC is still 0 volts. So according to the direction we chose, which is, we chose plus minus, this was B, this is C, this is VR4. Okay, C is 0 volts and VB is minus 52.857 minus 0. So VR4 is minus 52.857 volts. Okay. When you show me this work, I can look at this minus sign and I can look at this voltage polarity and I can still award full points because that is correct. Now I can state that my resistor voltage is negative means my actual polarity for VR4 is flipped. Does that make sense to everyone? Let's take a 10-second pause. You think over that. Let me know if you have any questions. Any questions at all? Does that make sense? Yes.
Does that mean all of our current?
Yes, that is correct. So the question being asked is, if the voltage polarity is indeed flipped or opposite of what we assumed, then doesn't that mean that the current is also flowing in the opposite direction? And the answer is correct. The answer is correct. The current direction would also be flipped. So if I asked you a question like that, that would be the answer you would give me. Now, if I chose A as my reference, then VA equal to 0 volts. My answer for VC, what would be the value for VC? Absolutely. The level between the two would not change. The level remains the same. My VC value would now be plus 13. So it'd be plus 13.569 and VB in this case. So if there was a different student who chose A as a reference, The R value for VB would be different. It would be 39 point, what would it be? 39.3 something. 398. 39.398. Okay, so VB would be minus 39.398. So let's say you chose C as the reference and she chose A as the reference. Your answer for VB would be minus 52. Her answer for VB would be minus 39. But both answers are correct. Okay, so again, I repeat, it does not matter what node you choose as your reference node. Your answer will turn out to be correct at the end. Okay, if you just compare nodes and say, hey, my node voltage is different, how come yours is different? Well, that's the reason. Yes.
So, as you know, where you select your reference nodes are all in reference. They're all in reference.
That's the baseline. Yes, that's the baseline of measurement. We are measuring all other voltages with reference to that baseline. So that baseline has to be 0 for the purposes of only this analysis. That's it. As I said, you can practice this problem. You know the answers, right? You can practice this problem with your reference at A. You can practice this problem again with your reference at B. Okay. The equations, again, the equations will not change unless you change the direction of the current. Okay. The current direction you could possibly change depending on, which node you choose as your reference, but they don't have to. You can still keep the currents the same. Yes. Mm-hmm. No. So it does not matter which node we choose as reference. Yeah. So again, same thing here. If you choose A as the reference, values would be different. For the resistor voltages, the levels between the 3 nodes remain exactly the same as what we obtained over there. That doesn't change. Yes. Mm-hmm. Just knowing it is fine. So the question being asked is, if we end up with a negative answer, should we show the change? And the answer is no. I mean, I can look at your circuit diagram. Basically, I can look at this and I can look at this answers and relate the two. So you don't have to redo your diagram or anything like that. So at the initial, at the beginning of the setup, beginning of the problem setup, you will have your circuit diagram. You will show me where the node voltages are. You will show me where the reference node is and the current directions. And I can take that, relate it with the final answer, and then, what credit that way. Oh, almost out of time. Yes.
So just double checking, when we draw the schematic, you want like the original one that we did not, corrected one? So like, since I got negative 52, could I just draw the correct direction and be like, negative 52 equals this direction?
Not necessary. It's not required. Again, I mean, I can take a look at it and infer that the answers are correct or incorrect. Okay. I think we are almost out of time. Didn't want to do the homework. Voltage source and super node. Sounds like something from a Marvel movie. It's not. It's a shortcut. Okay, super node is a shortcut. Like voltage division and current division, super node is a shortcut. So if you have a voltage source in a circuit, you choose one end of the voltage source, and boom, you have an answer for 2 of the nodes in the circuit. But what do you do if you have more than one voltage source in the circuit? You can't write a KCL express. You cannot apply Ohm's law and express in terms of a resistor voltage, right? The voltage source doesn't have any resistance. So you can't write a KCL expression. So it's a shortcut to eliminate the voltage source from one of the equations. So we choose one end of one voltage source as the reference. Then for the other voltage source, we apply the shortcut that is known as super node. Essentially, all you're doing is you're applying KCL at both ends of that voltage source. That's all you're doing. So if you have to leave, you can go ahead and leave. I'm just gonna finish this slide, and the recording will be there online. So let's say I wish to apply a super node around the 15-volt source. All I'm going to do is I'm going to apply KCL here at this node 3. I will label this as IS1, label this as IR4, and let's see, say this is IS2. I will call this as X and this as Y. So this node is Y, this node is X. Apply KCL at X. IR1, IR3. And this is IS1. Oh. IR2. Okay, now I have everything down. Okay, so apply KCL at X. At X, I have two currents coming in. So I have IR1 coming in plus IR3 coming in and IS1 leaving. Now, the point was that I can apply Ohm's law to IR1 and IR3, but I cannot apply Ohm's law to IS1, which is the current that is flowing through that source, right? So what I'm going to do is I will write another KCL expression at the other end of that voltage source. So I would apply KCL at Y. And when I apply KCL at Y, I have IS1 entering Y. I have IR4 also entering Y, so IR4. And then I have IR2 leaving. Okay, IR2 leaving. That's the bottom node. So now rearrange the terms, and I get IS1 is equal to IR2 minus IR4. Let's take a 10-second pause while you think on that. There's node X at the negative end of the 15-volt source. There is node Y at the bottom, which is the positive end of the 15-volt source. I have three currents at the top. I have three currents at the bottom, three connections. IS1 is the label I chose to give the voltage source, that 15-volt source. When I apply KCL, I obtain two currents entering at the top, one current leaving, which is IS1. When I apply KCL at the bottom, I have two currents entering, IR4 and IS1, and then one current, IR2, leaving. I can express all of them except for IS1 in terms of the resistor voltages. So what I'm going to do is this. If A equals X and B equals X, I can conclude A equals B. So you combine both equations together, and I can state IR1 plus IR3 is equal to IR2 minus IR4. And that's it. Super node is a shortcut that allows you to skip over these steps. That's all it is. It's a concept. It's a shortcut. All you're going to do is you draw a loop around this and you combine both nodes together. So basically, what you're going to do is you're simply going to take your resistors. You're going to short out that voltage source. And that's it. Super node means you're just shorting out that voltage source. You remove it from the circuit and you connect a wire in its place. So that way you have a current coming in, current going out this way, this current coming in, and this current leaving. So we eliminated IS1. That's it. The super node is you just draw a loop around it, place a short circuit wire across that voltage source, and you apply a KCL. So you treat it as one single node, but because there's a voltage source in there, we call it a super node. Okay, we'll end class here today. Thank you for your patience. And again, office hours today from 4 to 5, not between 1 and 2:30. Okay, so if you have any questions, reach out to me. Send me an email. I'll be able to answer emails before 4 o'clock, but I'll be in my office after that between 4 and 5.